of the previous one. Okay, so we were trying to discuss the solution on the Bethe lattice. And so we took a Bethe lattice of coordination number 3. This is the origin. And then there are other sides. So I define the partition function Ax is equal to sum over all possible animals weight of an animal. Okay, it's just introducing some extra notation. We're doing the same thing as what we did yesterday. And so the weight of an animal is x to the power size of the set A. The animal is a set of sides, so you can think of it as a set, and this is the number of elements in it, and this is x to the power A. So now this is a polynomial because it is a sum of powers of x, and we wrote it down as x plus 3x squared plus 9x cubed plus like that. So you can determine it. We wanted to know what is the coefficient of x to the power 30. So it's a little bit tiring to actually sit down and enumerate all the possible configurations with very large value of this power. But let me pretend that I'm going to do it. So let me write A of x is equal to summation over A1, A2, A3, where A1 is this branch and A2 is this branch and A3 is this branch. So if I sum over all possible choices of A1, A2, A3, that is the sum over all possible choices of A, right? And so this one, so if there is an animal which is made up of this side plus this plus this plus this, is so x times, now I want to sum over all these things. So maybe there is nothing here. So this will be called 1 plus, then you sum over all possible these things. So this, so we called it B1, B of x is the sum over all possible clusters which are growing on this sub branch from this tree downwards, from this top side downwards. And then I sum over this and sum over this, but this sum is the same as this. So the answer will be same 1 plus bx. So this thing gives me 1 plus bx cubed. This technique is called generating function technique. It's very useful because the problem of calculating A has been reduced to a somewhat simpler problem of calculating B, which only sums over one branch. Okay? So now I calculate B of x. Sorry?
Sum is gone. The summation is gone.
In this one?
No, that summation A1, A2, A3 is gone. No.
Yeah, the summation is gone. Sorry, I beg your pardon. I should have written one. Yeah, so the summation is gone. Maybe I should write it in 2 steps, but okay. So now I want to sum over B. So I start with this, and maybe they just top. But then there are 2 branches, both like this, and the weight of each is B. It's the same problem again. If I come here, I sum over everything below, that's the same problem as B. So this is 1 plus B whole square. And now this becomes a quadratic equation in B, and we can solve it, and I think the answer is written here. Okay, and so it solves the full problem. This part we did, and then there was this infinite connection to infinity. The other quantity I want to study in this problem is the probability that from this side there is one path all the way to infinity. Okay, again I do it in parts. I say starting from this point along this branch there is a path to infinity, we'll call it something, and this probability that there is a path from here is reduced to the problem of calculating there is a path along this path, this branch. Okay, let us call this all connection all the way to here. This will be called B, we have already used. What did I use here? We called it B infinity. Okay, so if there is a path from here to infinity, 1 minus B infinity is the probability that there is no path from here to here, and then you take 1 minus B infinity whole cubed. That's the probability that there is no path either here or here or here, and you subtract that from 1, and that is probability of the infinite path. Okay, and by a similar argument I would like to write B infinity. So I take this branch and there is a path all the way to down from at least one of these two. So you can say that there is a path along one, also there is a path along the second. So this is actually, we can just write it 2B infinity minus B infinity squared. This is double counting and you subtract 1. And I go to write a P so that the top side should be present. Then I can do this calculation, and you can solve this equation by realizing that one root is 0, which is the solution, which is the correct root when P is less than half. But if P is not less than half, then this P infinity as a function of, sorry, let me start with B infinity goes like this, and P infinity also goes qualitatively like this. So that solves the problem on the Bethe lattice. Okay. Now we will come to this lecture. Can I get out of this? The other second, can you put the second file on?
Shall I close this one, sir?
Yeah, close this one. Okay, so now we come to what I planned for this class. So cluster enumerations. So one of the things we have to learn to do in percolation theory is to look at the size of different clusters and study their properties. And one of the first things you do is what are the different possibilities. So that is called enumeration, cluster enumeration. So the key simplification in the percolation problem is the fact that all local properties of this system are easy to determine using a finite algorithm, even if the system is very big, but I don't care. If you are asking me what is the probability that this site is present, that has a simple answer. It doesn't depend on how big the system is, where is the boundary and all that kind of stuff. Okay? So we are taking square lattice, and we pick a randomly generated configuration of the system at concentration P and denote the probability that the origin belongs to a cluster of exactly S sites is probability of S. Okay? So then I would like to know what is probability that S is 0. It's easy because that site should be absent. Then we'll call it is a cluster of size 0. and so the probability is Q. What is the probability that S is 1? Well, this side, sorry. So I am taking a square lattice. I pick this side. This side should have a cluster of size 1. Means this point should be present and all these 4 should be absent. So the probability is P into Q to the power 4. So probability that S equal to 1 is equal to PQ to the power 4. Okay, the next one is a little bit harder. I would ask what is the probability of cluster of size 2. So the cluster of size 2 can occur like this. This is present and this is present, or this will be rotated in one of the other possible neighborhoods. But each of these occurs with the probability that these sites are absent. Otherwise, it's not a cluster of size 2, it is bigger cluster. So this becomes P squared Q to the power 6 and 4. And with a little bit of work, I can work out probability of S equal to 3, 4, 5. And I would encourage you to, just as a practice, do it up to 5 at least. It's a little bit of work, but it helps you think about the problem more concretely. Okay? But then, if I ask you for clusters of size 10, there are many clusters of size 10, and it becomes hard to do this. But anyway, explicit expression for prob S can be written down. And I can tell that, okay, suppose you have S equal to 10, then it will be a polynomial in P and Q, but Q is 1 minus P, so it's a polynomial in P. And the lowest power of P in that polynomial will be 10, because there will be 10 sides. And then there will be some powers of Q, which can be written as 1 minus powers of P. Okay. So there is a finite number of connected clusters containing the origin having exactly S sides. So I can have some clusters which have external perimeter T. Suppose I have a cluster. Okay. The external perimeter is the sides which are external to the cluster, which are not part of the cluster, but are neighbors. So they are called external perimeter. The sites which are in the cluster and they are connected to the boundary are called internal boundary, internal perimeter. Okay. So right now we are looking at external perimeter, and so if their external perimeter is T, then the weight is P to the power S, Q to the power T, it's a polynomial, and AST is the number of clusters with exactly S sites and exactly T perimeter sites. Okay. And sometimes we like to sum over T and just write A of S is, I don't care what is the perimeter, just total number of clusters of size S. Okay. So these are called animals which we discussed before. So now, suppose I give you, I want to determine what is the number of clusters of size 10 on the square lattice. This number is kind of a biggish number. So in the end, I will expect you to make a list of all possible clusters, and the number of elements in the list is a little bit big, 10 to the power 4, right? So I want to ensure that in that list there is no repetition and there is no omission. You will give me a big list. How will I check that this particular cluster has not been listed? It's a little bit of work, and firstly, even if you take clusters of size 6, it's a bit hard to ensure that you haven't missed out anything. Okay? So can I do this systematically? That is very important to do. And so it turns out that unless you systematize, it doesn't work. And in order to systematize, you have to learn to sort of work, what is it called? Algorithmically. You should have a particular prescription which works all the time. So I just remember when we were children, we used to play cards, and you are dealt out a hand, and you have all these hard spades, clubs, whatever. And first thing I want to do is I want to put all the spades on one side and hearts and diamonds and clubs. And as children, we just put this here and this here and this here and this here and keep on doing. Sometimes you put something here and then put it back and then do it like this. So if the number is small enough, you actually manage in the end. But if the number is 100 cards, then it actually takes a long time to sort them out into some proper structure without too much work. You can keep on doing and eventually you will somehow get there, but not necessarily where. So we want to discuss enumeration which is efficient and which is guaranteed to work right. Okay, so no omission, no repetition. And so the way to do this is to give each cluster a unique identifier. For each cluster I will give a name, and that name will be specific to that person. And so then you take all possible names and make them an alphabetical list. Then I can ensure. So like there are so many people in India, everybody has an Aadhaar card number, which is an identification number. So everybody has a different number, even though there are billion people. You can sort all the people in a list using their card number. Okay, that is the reason the card number is a number and not a list of other characters. So we will do the same thing. We will assign a number to each cluster. So I take a cluster which is, let us say, a complicated looking cluster. My origin. So what name shall I give to this cluster? You can imagine the cluster in 3 dimensions or in 4 dimensions. And then it becomes harder and harder to decide how to give names to these clusters. The name should be unique. If I give you the name, you should uniquely identify the cluster. So it's possible. What all I do is, these are sites, no? This site has a coordinate 0, 0, this site has a coordinate 0, 1, 0, 2. I give you a list in which all the sites are given, and that's a name. Unfortunately, that name is kind of tricky, and if I give you there is a list, and in the list which number comes before which one, you should decide again. You should make alphabetical listing of the list itself, right? And then you will have complications. But anyway, this thing is a complication, and it turns out that it is not very efficient. The reason is the name is very long. Each site will have D labels because you will give D coordinates. And there are many sites, and you will have S times D labels. But most of the sites are empty. So I don't really need that big a list. So what I will give, I will assign a number to each site and each perimeter site. Assign a label 1 to something to each site or perimeter site. Okay, so I start with the origin. The origin is assigned a label 1. Now this site is occupied, so there must be at least one occupied site in the neighborhood of its nearest neighbors. So which ones? Maybe this one and not this one but this one, and so on. So some of the neighbors of this site are occupied, some are not occupied. So we will just label all the neighbors of this site. 2, 3, 4, 5. There are many neighbors. I have an ordering list. East, comes before north, comes before west, comes before south. It's an arbitrary ordering, but I have decided. So first neighbor of 1 will be called 2, 3, 4, 5. Now some of these sites are occupied, some are unoccupied. So I will look at the first occupied site. Okay, so that is number 2. Then I look at all the neighbors of 2. Some of them have already been labeled. The ones which are not labeled, I will label now, using my same rule. So 5 has been used up, so I will call this 6, I will call this 7, this is already labeled, I will call this 8. Okay? Then I go in this list. So 2 is an occupied site. I look at the next occupied site. 3 is not occupied, 4 is not, 6 is occupied. So I look at all the neighbors of 6 and label them. So 6 will have, 8 is used up, this is 9, this is 10, this is 11. Then I look at the next occupied site with the lowest label, which has not been discussed so far, which I didn't visit. You know, I went up to 9, but I didn't go beyond this. These sites I haven't seen. I don't even know if they are there. Okay? No, I know this one because I went up to 6 and I know this is a neighbor of 6, but whether this is occupied or not, I am not sure. I go and look at it now, and this is occupied. Then I label all its neighbors. So this will be 12, 13, 14. And I keep on going this way until I exhaust all the labeled sites. And then I stop. Okay, this is the rule. You can do this in any dimension. So you start with the list, start with 1 at the origin. That's given here, actually given here. Start with 1 at the origin. All unlabeled neighbors of 1 are given next available labels, 2, 3, 4, 5. Then you go to the topmost unvisited occupied site and label all its unlabeled neighbors, and then go to the next one and the next one and so on. It's done. What I have produced is a label for each occupied and perimeter site. And this labeling is unique by my algorithm. Yes, sir.
So when we are labeling the 3 sites,
Hmm.
let's say if I have went to 1, 2, 6, 9 and 12 and 11,
Hmm.
but I was going in, let's say right hand direction,
Hmm.
but I labeled the 11th site,
Hmm.
which is neighborhood of 6, but I didn't label 14,
Yeah.
and the neighborhood of 11 within the below it.
No. So you have to label systematically, as we decided.
I am saying that when I go in this direction, I will have to come back and go in down.
Yeah. No. So as we said, the rule is go to the topmost unvisited occupied site in the list and label it. Okay? No other way of is allowed. And then the point is this: if I give you the so now the name of the cluster is 1011001 0, where this one says that the label number 1 is occupied, label number 2 is occupied, label number 3 is not occupied, label number 4 is not occupied, 5, 6, 7, like that. This is a finite list because the total number of things I have labeled is going to be finite, and they are just sequence of 1 and 0. And if I give you this sequence, you can reproduce the cluster. I will start with 1. Then this tells me that 2 should be occupied, this should be empty, this should be empty, and so on. It's done.
Okay, here you have done for 2 dimensions, but for 3 dimensions there are 8 neighbors.
6.
Oh, 6, sorry. So then
Same thing, 6. You just label 2, 3, 4, 5, 6, 7, like that. The method works for arbitrary graphs. They don't even have to be regular graphs. Okay?
Slightly confused. So if let's say one site has 2 neighbors
Hmm.
which are occupied,
Yeah.
well, like in this case 12 is the node
Yeah.
which has 2 neighbors.
Yeah.
Where do you go? How do you decide?
So we said this rule.
Yeah.
There is a priority rule. Which neighbor should be listed first, which neighbor second.
You'll go to the right first, right?
East first and north, I will go here and label it by something.
After you go to the right side,
Hmm.
you reach the end. Now
No, you don't reach the end. You just label the right side. Just that neighbor. उसके आगे क्या होता है मुझे अभी नहीं देखना है. I keep on labeling more sites, but always in this preference order. Go to the topmost undivided site and look at its neighbors. Okay? Topmost in the list. The list is 1, 2, 3, 4, 5. This is the list of sites I have labeled. I don't have to give them coordinates. In my head there is a list. So the site with the lowest label is the topmost site. Okay, topmost unoccupied site, unvisited. Means I haven't seen whether it is occupied or not. See, if I give something a label, I'm not always sure it is occupied or not. When I come to that site, I will decide if it is occupied or not, right? After 9, I will go to 10 and check that it is unoccupied, then go to 11. Yeah, right. Sorry? No. So this is the way I will do it. This is the rule. You can take some other rule. It doesn't matter, but it should be a unique rule which assigns a unique name to each cluster. And given that name, you should be able to determine the cluster uniquely. One-to-one assignment of names and clusters. Yes, sir.
Just a follow-up on the previous question. So, even right now when we're labeling sites, we only end up labeling sites that are either on the line of the origin, one above or one down. So, what happens when we reach the end? How do we label the sites that
Okay, no. So let's go on. Let's go to this one and this one. This is my cluster. I'll go to 12, 13, 14. And so I have labeled up to 9. And then I go to 11. And this will be labeled 15. Then I go to the next available site, which will be 11. And it is been labeled. So 12. 12, I will label this 16, 17. Okay, then I will go to this one. It has only this side below it, which is not labeled now. It will be labeled 18. Right? Then I will come here and label these accordingly. All sides, yes, sir. I don't know, this is not a unique prescription, but it is a choice, but it is a choice which gives a unique way to go proceed. And it allows me to reproduce the animal once I know the name. You can change these rules. You don't like this one, I like W here, N here, this will work equally well. Yes, sir.
So by doing this, we are considering only clusters that are connected to the origin.
Yeah. So, I took all the clusters these are rooted animals, which are, origin is by name the site which I start with. Okay? So, yeah, so each rooted animal has a unique name. Otherwise, if I choose the origin here, then this cluster will have a different name.
Because we only label the occupied sites or also the unoccupied sites?
The neighbors of occupied sites. Okay. So, very good. So, this gives you a unique name. Now, there is a list of possible names, and some names are not possible. So, I can take something called 1, 0, 0, 0, 0, 0, 1, 1, 1. This name does not correspond to any animal, because if I start with 1 and 2, 3, 4, 5, all of them are 0, then you cannot grow. Okay? So, there are some words which are not possible names of anything. So, they are not possible animals. This is just like in any language. You can make a string of characters. Some of them are allowed words and some of them are not allowed words. So, then we have a list of allowed words, and we can take all allowed words of length less than 10 and arrange them alphabetically. Okay? And I can make this dictionary if you ask me to make a list of all possible names of length less than 10, then I can make these dictionaries. So I will start by, okay, that's what we are going to do eventually or now. So this is assigning unique names to clusters. Okay, we have done this. Now comes the second part, is that I want to make a list of all possible allowed names efficiently. Of course, I can make the list, but can I do this efficiently? Okay, so it's like this. There is a general strategy in computer science which is called depth first search. This is what we will use in our problem. This is a general strategy, but it's like this. Any computer algorithm or anything I do can be written as a decision tree. I start here, I go down. I have two choices. I can go here or here. Okay? When I come here, I have some choices, and I take one of them. Then I go to that one, and then I still have some choices. I go below. So, for example, I started with something called 1. Then I have a choice whether 2 is occupied or not. So, this says 2 occupied, and this says 2 unoccupied. Once I go to 2 occupied, I have a choice whether 3 is occupied or not. Okay, and keep on going like this. Okay, so every time this will be binary search here, but more generally in a tree you can have several options at any given time, and there is a decision tree. You take this branch or this branch or this branch. Now the question was, can I make a list of all possible ends of these things in a sequential way, possibly? So the way it goes is that depth first search is go to the depth and stay to the left as much as possible. I have made a tree. So the tree can be written on a two-dimensional graph. Okay? And so I will define a notion of leftmost. The notion, priority rule N, E, W, S was the priority rule. If I have several choices, which one to take first? Okay, so I take this one. So it says go to the left, then go to the left as far as possible. If you cannot go any further, then just go back one step and erase this. Then go left, go here, go left, go here. Now you cannot go any further, go back up and erase this. You are here. It says go left, go down. You cannot go further, then go up and erase. And now the leftmost becomes this, and once you come here, then you go up here, then you cannot go any further down. Then you go up here and you go here and so on. So this is what the robots do when they run in a maze in 2 dimensions. Go left as far as possible, and if you cannot go any further, then backtrack. It is called backtrack. Okay? And this is what we will use in our problem to generate the full list. See, the point is the argument is logically very clear already. I have told you the rule. But now you have to actually implement it. You have to write a computer program which does exactly this. When you come to a site, you decide to occupy it. That is the preferred option. Once I go to 2, I first make all animals in which 2 is occupied. Then I remove, then I say 2 is not occupied. And then 3. First I make a list of all animals in which 3 is occupied. Then make the list with 3 is not occupied, and so on. Okay, and this list will end. So we said that if you have a problem in which each site has at most 4 neighbors, okay, So then the number of perimeter sites no, number of sites plus perimeter sites is, so if I take one site, it is 1 plus 4, 5. My list will be 1 with followed by 4 zeros, and then it will stop. There is nothing more. If I have two sites, it will be 1, 0. So this site is label 1 and is occupied. But if this one is occupied, it is 1, 1, 0, 0, 0, 0. Like this. This is the second animal, which is this one. It's 1, 2 occupied and all others are unoccupied. But then I can go to this one, which is 1, 1, 0, 1. And then these are the other sites which are unoccupied. And so it will be followed by zeros, and so on. See, actually you will have to work with this a little bit because it is not so trivial. But the logic is very simple and clear. And if you have a clear head, you can do this very well. Okay? Very good. So this one is called depth first search, and it is also called backtrack. See, whenever I go depth first, whenever I cannot reach, when I cannot go any further down, then I erase the last step and continue. Okay? So this is what the algorithm does in the end. So this one says that so if I make there are that many perimeter sites, and the total number of list with the characters in my list will be only 3s plus 2 at most. Okay? So it's a finite string of that length. How many binary digits are there with that length? 2 to the power that number. So the total number of animals of size s is less than or equal to 2 to the power 3s plus 2. And of course you can extend this argument to any other lattice. Okay? And it is actually quite efficient because I ask you to do better than this. This is the upper bound on the number. Can you produce a better upper bound than this? It's possible, it can be done, but it is not so easy. I will leave you to think about it because of course we have done some very sloppy argument and we gave this bound, but can you do better? Yes, but not so easily. Okay. So I want to spend a few minutes on the backtrack algorithm because it's an important idea. So we have already explained this stuff, but I want to give an example which will just fix the idea in your head. And this is called the 8 queens problem. It's a very standard example for backtrack in computer science, but some of you or most of you may not have seen it, so it is good to tell it here. Okay, so the question is the following. You have a chessboard. Chessboard. Too much? Like that. And now you have to put queens in this chessboard so that they don't attack each other. Now I can put at most 1 queen in each row because if I put 2 queens in one row, they will attack. So I can put at most 8 queens. But can I put 8 queens? Because if I put some queens, they might attack diagonally, or they might attack along the vertical or some such thing. So the question is, how many ways can you put 8 queens on the chessboard so that they don't attack each other? And the answer is, there is actually a way to do it. And actually there is a large number of ways you can put 8 queens on the chessboard. How many ways are there? I don't remember the number offhand, but it is 200 something. So can you produce a list of all allowed configurations of queens, 8 queens not attacking each other on the chessboard? So the answer is like this. So these are the sides of the lattice. I will label this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. First queen, let me try to put it here. Okay? So I start by putting it here, then I cannot put anything here. Can I put it here? No, no, yes. I put the second one here. Then I cannot put anything here. Put the third one here, no, 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 no. Yes, I put this here. Okay? Next one, no, yes. Then this one, no, yes, no. I cannot do it here. Next one here. No, no, no. Yes. Very good. Oh, maybe, yeah, very good. So this one here, and then this one, no. No, it attacks from here, it attacks from here, this. This one attacks from, does not attack, very good, it's working. And then this one, here, no, 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 no. All these are fields, so that won't work. This won't work. And this one is going to be attacked by this one. Yeah, it attacks by this queen. So this is not possible. Okay? If this is not possible, I cannot put any queen on this row. If I cannot put any queen on this row, it is not going to work. So I just say that, okay, this is not possible, means this position is not possible. Suppose I fix all these, then this cannot be placed here, because there is no possible completion. Then I try this one here. Unfortunately, this one is, I think, going to be attacked by this, so it's not possible. Then I try this one. This one is also not possible, it is attacked by this. Okay? So I cannot complete this. So then I go back and say, this is not possible, this should be placed at least in this position. And you keep on going like this. It turns out that within about 15 minutes of actual work, you can generate all allowed configurations of 8 queens. It's a lot of fun actually, it is not much work, it's a lot of fun, and you should do it because it fixes the idea of backtracking in your head completely. Okay? And then I'm saying that we just do the same thing on my decision tree. Whenever there is nothing possible, you erase and go backtrack. And so this part of the thing I will not do here. I have given the theoretical idea, and the implementation of it into C program or Fortran program or your favorite Python program or whatever will not be discussed here. But there is actually an existing 40-line program which does this. And it's actually very cute because it's very powerful. It works not only on the square lattice, you can take the triangular lattice, you can take 3D lattice, whatever lattice, and it will give you the correct numbers to arbitrary size. Okay? And that you can do it in 40 lines is very impressive. You know, sometimes people say that the soul of brevity is the soul of wit, and it's also the soul of literature. But brevity at some time is also the soul of understanding. If you can understand something very well, then you can write a 40-line program. And if you don't understand it well, you will perhaps write a 500-line program doing exactly the same thing. Even if it is correct, it is not enough to write a correct program. If you can write a 3-line program, why are you writing 50-line program? It shows lack of understanding. Okay? So that is why you should actually look at this program and understand how it works. It is not trivial. To understand the program maybe take you 2 hours or whatever, but it's worth spending that time because you will have learned something new. Okay, so we go on. So we have given this bound, and sorry, we have already given an upper bound on AS. It can only grow as 8 to the power s. But now I want to give a lower bound on AS. How does it grow? So it's very trivial to say it must grow at least as 2 to the power s, because if I take a site, then I can always grow in one of the 2 forward directions. And then I go there, then I can grow in one of the 2 forward directions. And then keep on doing like that. So the number will be at least 2 to the power s. Okay? This 2 cannot be changed into 3 just like this, because if I grow in 3 directions, then sometime I may come back and I may not be allowed. If I change 2 to 3, all the choices are not allowed. But of course, you can improve on this bound also, and it's interesting to see how to improve this bound. But actually it turns out that there is a very good upper bound on this, which is, if you consider this Bethe lattice, which has coordination number 4, then that gives you the maximum possible number of clusters with 4 coordination number graph. Because otherwise what happens is sometimes 2 of the things which in the tree graph I gave labels, they might actually share the same label. So then that choice is not allowed. You will say, that branch of the tree is lost. And so the bound is AS is less than equal to number of S animals on the tree graph with same coordination number. Okay, and this bound is saturated because of course on the trees it is everything has coordination number and this is the number, so you cannot do better than this. Is the best possible bound. Okay. Sorry. Yeah.
What is the theta value?
No, so very good. So it turns out we have shown by this argument that AS can grow at most exponentially and at least exponentially. So the guess is that it actually grows exponentially unless it does very wild oscillations, which actually doesn't happen. Okay? So it grows exponentially. The log of AS will grow linearly with S. What is the leading correction term? The leading correction term could be a sublinear power of S. Turns out that usually in most of the problems we have studied, it is not, and it is only log S. The leading correction is log S, so that the animal numbers actually grow like lambda to the power S into S to the power something. Okay? The proof that this is the most general behavior is interesting, possible, actually not there, because there are some slightly funny graphs for which it is known that the number is not this and the correction term can be subleading exponential. Okay? So those are funny systems. Here, if you calculate A of x, that will have a power law singularity at the end point of, as a function of x. But if you had AS grows like lambda to the power s, mu to the power root s, okay, then you calculate A of x is equal to summation AS x to the power s. This converges for x less than 1 by lambda. But how does it diverge? Near AX goes as exponential 1 upon x minus xc minus x to the power some power half. Okay? So it is very strongly divergent. It is possible. These are called essential singularities of A of x as a function of x. but they are not encountered in many problems, at least on a regular d-dimensional lattice they don't occur. So we will take that this behavior is not generic, and the behavior which is generic is lambda to the power s multiplied by a power law correction. Okay, and so the exponent theta, it's interestingly turns out to be universal, in the sense if you take all two-dimensional graphs, square lattice, triangular lattice, whatever, then you get the same value of theta. If you take some other dimension, then it becomes different. Okay, so just like the critical exponents for the Ising model are universal, for all two-dimension graphs you get the same number, but three-dimensional Ising model is different. Same way, the exponent theta for all two-dimensional graphs will be the same, and for three-dimensional graphs will be different. Lambda will be different for different graphs, but this exponent does not. Okay, all right. Yeah, the value of theta in 2 dimensions is known. It is 5 by 6. We will discuss it actually later. Okay, so now we are going to derive some results, actually hand wave through, but give you the essential argument of results, which are proved in very complicated way in some mathematics textbooks. So they give you a long proof about what is written here in blue line. We say for all p less than 1 by lambda, probability of s decays exponentially with s. Okay, so this is hard to prove, but okay, it's proved in 2 lines above. So the actual function is prob s is p to the power s q to the power t a s t, but q is less than 1. So the largest value it can have is 1. So it's less than equal to a s p to the power s a s. But p to the power a s goes like lambda to the power s by definition. So for all x less than 1 by lambda, this will be convergent, exponentially convergent. Okay? End of proof. I think it's important to realize that this point is not so deep, right? It will turn out that many other proofs we will give subsequently will be equally easy. Maybe it is actually deep, but it is straightforward to prove. Okay? All right. So now we can show that the 2-point correlation function, if I take the percolation problem, and take 2 points A and B, which are at a distance r from each other, what is the probability that these 2 points belong to the same cluster? That is a typical 2-point correlation function we will discuss. In probability theory, this is the 2-point correlation function. So the proof is that for p small enough, then this decays exponentially with r. Okay? So what is the proof? Well, if this point is connected to this, there must be a path going from A to B. Okay? So the path can be slightly complicated. It looks like this. There might be actually stuff like this. There is more than one path. I can take this path or I can take that path, but there is at least one path. So I'll pick one path and I will say that the probability that A is connected to B is less than equal to the probability that A is connected to B using path P summation over with path P present. Okay, this is path. So paths are, this stuff. They are called self-voiding walks. You don't allow any loop in the path. because it's not needed. Yes. Yeah. So some configuration will be counted more than once in this summation, but it's a bound, so it is allowed. If I count it more than once, I will only get a bigger number than the real one. So the right hand side is bigger. Right hand side is sum over all paths, but sum over all paths may be double counting. Okay? But now if there is a path of length L, then the probability that this path is present is p to the power L. Okay? So this is p to the power L of path. Okay? But L of this is summation of all paths, but these paths have a lower bound on L. L cannot be smaller than something to reach B up to B. The smallest number is actually the distance between A and B. That is called the lattice distance. If you have 2 points like this, from here to here you can only reach in 2 steps. One step is not possible, 2 is possible. We will not worry about root 2. This is not the Euclidean distance between points. It is the path distance, the length of the shortest path. And that is, we will call that R. So this will be summation P, L of P bigger than equal to R. But now I should write times the number of paths of length L. But number of paths of length L grows exponentially with L, with some coefficient which is usually called self-avoiding growth constant, mu to the power L. So if P is less than 1 by mu, this series will be convergent and it will decay exponentially with L. End of proof. We didn't prove that all the way up to PC it will grow exponentially with, it will decrease exponentially with L, but we have proved that for P small enough, this 2-point correlation function decays exponentially. So there is very small probability that you will go far enough. Okay? The next step in the proof will be that if P is big enough, P is near 1 or P is bigger than PC, then if you pick 2 points very far, there is still a finite probability that they will actually be connected. Okay? So that is important to establish as a, so like in the Kesten's quotation which I gave in the beginning, they said that if you want to give a proof of a result, it usually requires some new technique. So how do I go around proving that if 2 points are very far, they will still be connected with a finite probability, right? It requires a new method. I mean, I'm not inventing it. It was done by somebody else. I can learn about this. But the person who thought of it first must have been very smart. Okay? That person was Piles. So we will, so number of self-avoiding walks I said is less than 3 to the power L. Then if P is less than 1 by 3, GR decays exponentially with R. That is the proof. Now we want to give this Piles argument that if P is large enough, then the probability of infinite cluster is bounded above 0. By which is meant I pick a point at random, the probability that will be connected to sites arbitrarily far away remains non-zero, positive. Okay? And this proof is interesting. It is a variation on the proof given for the Ising model. Piles actually gave it for the Ising model. I am changing it to the percolation model, but the proof is the same. Okay, and let us go through it because it's interesting and important and non-trivial proof. So we consider site, my time is up, half an hour, very good, so we can continue. So site percolation on the infinite square lattice with density P of occupied sites. If the origin belongs to an infinite cluster, there should not exist any simple closed loops of unoccupied sites that surrounds the origin. Okay, so I have a big lattice, and this origin is connected to some sites very far away. Then there should not be a closed loop of unoccupied sites. All these sites are unoccupied. Then you cannot go from here to infinity. Okay, it's as simple as this. So it comes to the 1 minus probability of infinity is less than equal to summation over all possible closed loops, the probability that the loop is actually all empty. You again overcount, because if given a site which is not connected to infinity, it might be, there may be more than one loop. There might be a loop like this. Okay, so here is my system, this is this origin. These sites are unoccupied. There is more than one closed loop, but I will overcount, it doesn't matter. I am just giving an upper bound, sorry, lower bound in this, upper bound on the number of such clusters and lower bound on the number of the opposite type, of course. So, okay. So, first thing, let NL be the number of distinct shapes of closed loops of perimeter L. Okay. Then the number of closed self-avoiding loops is 4 into 3 to the power L minus 1. Because the first loop can be in 4 directions, next loop can be in at most 3 directions, and at the end of L you should come back to the origin. I overcount, I allow even things which don't come back to the origin, so that the bound is good. NL is less than 4 into 3 to the power L minus 1. Okay. So for a loop of perimeter L, the probability that all sites are unoccupied is q to the power L. That is simple and straightforward. So in this sum, there is an exponentially large number of terms, but each term is exponentially small in L, q to the power L, right? So if q is small enough, the chances are that the q to the power L factor dominates over the other factor which is growing with L. So then I got to write, okay, careful counting. So a perimeter, loop of perimeter L has an area at most L squared by 16 on the square lattice. You can check. But it's interesting. This is a, if you take a continuum 2D, then a loop of perimeter L must be a circle, and it has some area pi r squared, perimeter is 2 pi r. On the lattice, the number, there is no pi. So the number is actually the smallest circle on the square lattice is the square, where by circle I meant the shape which gives the maximum area. Okay, and so you can check that this is true. Now if I give you a loop of size L and I say that the origin must be inside it, then there must be at most L squared by 16 different ways I can put this loop over this, right? So then that gives me this bound here. This first term is the number of closed paths, second term is the probability of a path, and the third one is the number of ways, different ways the same closed path can be put on the lattice to surround the given site. Okay? And now I just stare at it this and say, oh, if q is, oh, and the summation over L, let's be careful, it is 4, only even lengths are allowed, 4, 6, 8. I don't want to keep the other term, but keep the even lengths. And then if q is small enough, then this sum will converge and converge to a quantity which can be made pretty small. Q to the power 4 is the lowest term you can write, right? So you can make it as small as you please, and so the left hand side can be made as close to 0, and the p infinity can be made as big as you please. It gives you a bound on p infinity. Okay? End of proof. We have proved more than just that bound. We have proved that p infinity goes to 1 as q goes to 0. Okay. So we showed that in the low density phase, the cluster size distribution decays exponentially. With, in fact, while the result was true for small p, one expects the result to be true for all p less than pc. Yes. Yeah. Yes. Yes. Yeah. So that's also allowed in the bound. Right? Self-avoiding loops also satisfy this inequality. A self-avoiding loop of perimeter L can have an area at most L squared by 16. Okay? Yes?
Typically, what is the factor of overcounting at that?
No, so very good. So this part in the sum can be actually improved easily. For example, I can take the first term and write it exactly because I know what is N4. So you write the first 5 terms exactly and use the estimate for the rest of the terms. I can actually calculate the first 15 terms by using the first 15 terms, which goes up to L to the power 30 or whatever, and use them to get a very good estimate and then use the bounds for the rest. And you get pretty close to the correct number. Okay. Yes.
What is the factor? I mean, we are overcounting because we are counting.
No, so in each of these steps there is overcounting. In the first one, this is 3 to the power L I wrote, but you can do this better than this. You can get mu to the power L. In the second one, you cannot improve on this, but the third one, you can improve because, okay, this is the bound. But if you put all that, the single term in which you do the best possible, L squared by 16, there is only one shape. So mu corresponding to that shape is 1, not 3. So, by careful counting, you can certainly improve on this bound, but we are not going to bother so much.
So in this Piles argument for the Ising model,
Yeah.
so there it's like you created like a domain of upspins or
Hmm.
whatever, and there's the energy cost and entropy.
Hmm.
So I don't see how it's related.
So very good. There is a cost of a perimeter. The probability that a perimeter has a particular shape is exponential minus beta JL in the Piles argument. Here it is just q to the power L. Okay, and the next step is how many different ways you can make the contour, which is the same. Okay. Okay, so it is believed. One expects this result to be true, and the probability that a cluster is bounded by exponential minus Cp times S, where Cp is a decreasing function of P. When you increase P, Cp decreases and goes to 0 as P goes to Pc. This is what I expect. This is what I expect means people have said before me. I'm not the first one to say this. But proving this rigorously for all the way up to PC may not be easy. In fact, there are some arguments which prove this, but proving this requires some 20 pages of complicated mathematical rigorous proof, which I am skipping just now. They use renormalization group theory arguments. So, if you want to extend the proof all the way up to PC, you have to actually develop a new technique. Piles argument will not help. Okay. So, in the regime P bigger than PC, the cluster size on an infinite lattice could be strictly infinite. P is bigger than PC. With some probability, the cluster size is infinite. But you can ask, what is the probability of finite large clusters of size S? I would say that clusters should not be infinite, but it should have actually 1 million sites and no more. Right? So then, how does P of S vary for large S? For a fixed large S? The answer is it doesn't vary exponentially, interestingly. It varies slower than an exponential. So this is just to give the sort of feeling that, whenever something decays to 0, it must decay exponentially or as a power law. No, it doesn't. In this case, it is known that it decays only as a stretched exponential. exponential minus cs to the power d minus 1 by d. D minus 1 by d is less than 1, right? So it is a slower than exponential decay. And the proof is not so new, but not so old either. I mean, percolation theory was defined in 1950 something, and this is occurring only 20 years later. So it took people long time to realize this. Okay, but okay, here is the proof. Consider a typical configuration of the system as p bigger than pc. We mark a, so we are working in d dimensions. And I just take a hypercube of linear size L, and by hand say that all the perimeter, all the boundary sides of this hypercube are absent. So it's q to the power surface of the hypercube. Now, if the origin is inside this, I can put this hypercube somewhere such that it encloses the origin. Then the cluster you make will be of size less than equal to L to the power d. Okay? But if P is bigger than PC, then the size will be actually, we have estimated before, it can be 0.9 times L to the power d because P infinity is quite close to 1. So if you make it big enough, then you can ensure that at least half into L to the power d sites are present inside. Okay? And then the bound still goes through. So it says probability that S is bigger than S0. So it should be S0 to the power d minus 1 by d. Okay? The proof is quite rigorous here, but there is one sloppy stuff which I didn't estimate all these numbers alpha, beta. How big should alpha be so that this works? Depends on P. I can write a function or I can give a bound on this, but we are not getting into that technical detail because the key idea is already presented.
So going back to Payal's argument, if
Yes.
we want to apply it in 3 dimensions,
Yes.
we have to think of surfaces?
Yes, of course. So there will be a bound which says that the number of surfaces grows as exponential of the surface area. Okay, and then there is a term which says that the probability of this surface is q to the power surface area. So the whole thing goes through, but you have to use the number of surfaces.
And this also generalizes to sort of non-regular lattices?
Yeah, everything goes through. With a little bit of variation, it just goes through. Okay, so now relation of percolation model to the Q state Potts model. So one can express the free energy of classical theoretical models, like the Ising model or some other model, I don't know, Baxter model or something or the other, as a large deviation function of the number density of clusters in the percolation model. So in the percolation model, we have said there is a lattice and there is a P and there is a number of clusters corresponding to P. There is a typical value and there will be fluctuations around this. But suppose I say, what is the probability that the number of clusters is actually twice the expected cluster number? That is called a large deviation. And the probability of this happening is very small. It is exponential minus the area of the sample. Okay? But exponential minus area multiplied by a coefficient. That coefficient is called the large deviation function. That's the general definition. And so that's what is written here. Let us consider the moment generating function of the rth moment of the total number of clusters. We define the large deviation function probability that number density of clusters equal to x. Number density means the actual number of clusters is x times L squared. Okay? Then there is a typical value of x, but if you choose a value of x which is not the typical value or is bigger than the typical value, then this function goes like exponential minus v times f of x. And then this f of x is actually related to the free energy of other well-studied models, like the Ising model. Okay? So this is what we want to show. So we start by considering a model where at each side there is a spin Si which can take q distinct, and for example q equal to 2 is the Ising model where the spins are up and down, and the Hamiltonian of the system is minus h jij delta function of sigma j. If there are two neighbors with the same type, both of them are type q equal to 3 or q whatever, same value of q, same spin, then there is a lower energy. And if they are unequal, then whatever be the, if this is 2, this is 3, this or this is 2, this is 5, the energy is 0. Okay, so that is by definition that is the Hamiltonian of the system I consider. So for this system, I would like to define the partition function and just calculate the partition function. That is what we are told to do in my class. So partition function z will be equal to 1 plus something depending on the delta function of sigma is sigma j, and product over all bonds, and then sum over all assignments of sigma. This product over all bonds gives you the, this term gives you this exponential of this weight function. So v is e to the power beta j minus 1, and then sum over configurations give you the, so the full product gives you exponential beta h, and then the summation gives you the standard summation. So now if you expand this product in powers of v and make a graphical representation of each term, you draw a bond if the Vij term is written, and don't draw a bond if 1 is written in the product term, and then you do it. Then the sum over configurations can be, or the product expansion can be written as, these are my sides, and this is my bond, and then all possible configuration of such bonds gives you 2 to the power b terms. B is the number of bonds, and then I sum over these, and then I sum over configurations. That gives me the partition function. But given a particular assignment of b, I can sum over S easily, because what is the sum over spins? It's just a product of, I'm summing over spins, but inside there is a delta function. It says this spin should be the same as this, should be the same as this, should be the same as this should be by independent. So each cluster gives you q possible assignments. So if you sum over spins, the sum over all the spins is q to the power number of clusters. Okay, so that is, so in the summation over spins, each term with C clusters gives q to the power c, and the partition function can be written as z vq is q to the power c v to the power number of bonds, because each bond has a v term. Okay, and now I sum over all possible assignments of bonds, this thing. So if you put q equal to 1, then you are just summing over assignments of bonds. That is sort of the percolation problem where each bond has a weight. But if you take this thing and just multiply by if you take this z of q, then when q equal to 1, then that was the percolation problem. But if you take dz by dq and then put q equal to 1, then you will pull out a term which is proportional to c. It will give you the average number of clusters. If I take two derivatives with q, it will give me average value of c squared, and so on. So the function as a function of q is sort of the generating function of the moments. Or if you get it for all possible q, then you expand in powers of q, you get all the moments of the cluster number c. Okay, so that is what we would like to do. And then I've got this log q. So then, sorry, it turns out that then you take a bigger V, then Z will be, log Z will be proportional to V in this general sum, because it is sum of term. There is a sort of general proof people give, but which I am not giving here, that you can see that log Z is proportional to V. So log Z by V, take the V goes to infinity limit, gives you a quantity which is a function which is called the free energy per site in this general model. Okay. Now comes the interesting point, that so this problem is defined when Q was 2 or 3 or 4 or 5. It gives me the free energy per site of the 2-state, 3-state, 4-state Potts model by construction. But when I look at this definition, I can put Q equal to 2.7 and it is well defined. The partition function is well defined for any real value of Q. It doesn't have an interpretation as a discrete number of states Potts model. That doesn't bother me. So I will say that I'm quite happy to consider Q to be a real variable and consider partition function as a function of Q, of the real variable Q. I think people do this in other cases also, like they take n vector model and then say, oh, but I can think of n as a real variable. Kind of boggles my head, but okay, if you want to do it, you can do it. I think the precise point is exactly this. When you think of the dependence of Z of Q as a function of Q, there is a real function Z of Q which coincides with the function you are looking for at the integer values. And then it is actually good to think of the real valued function as the more basic object. Okay? And so so that is called the Q-state Potts model. And this generalization of the Q integer Potts model was a great insight of Fortuny and Castellin. Again, it is sort of not so recent, but not so old work. It is not work done in 1950, it is work done in 1970. Okay, 20 years after the percolation model was defined, people were able to realize that, oh, it can be thought of as a particular case of the generalization of the Ising model or some such thing. Okay. The reason this Q-state Potts model becomes interesting is that sometimes you can get some results about the behavior of the Q-state Potts model for general Q using other techniques called the conformal field theory or whatever, which I don't know enough about. Okay. But turns out that you can actually write behavior of this function exactly for general Q, but only near the critical point. They will not be able to do it for general Q only in the continuum limit, only for near the critical point. You can say something about the behavior of the Potts model function for arbitrary Q, but that too only in 2 dimensions. So what happens for general Q in 3 dimensions? Okay, people are able to conclude something, but not too much, but there are good review articles and you can look them up, and we will not actually do it how. Okay, so I am close to the end. So these are just some exercises. So I will explain the exercises and then you will do them. So the first one is to write down the probability P of S that the origin belongs to a cluster of size S for S equal to 0 to 5. Write it down as an explicit polynomial of P in each case. And then the interesting point is that if you sum up all these numbers, P0 plus P1 plus P2 plus P5, it will differ from 1 only by terms to order P to the power 6. All the terms of order 1, 2, 3, 4, 5 will cancel exactly. This is right now it is being done on the square lattice, but you can do it on any your favorite lattice. This argument is still working. Okay, so I have actually tried to construct problems which do not invoke the square lattice to great extent. It is just whatever we do for the square lattice, you can do it for some other lattice, even the cubic lattice most of the time. This argument will work on the cubic lattice also. Okay, next, how well can you improve the piles type proof given here? It's perhaps not a very imaginative exercise, but sometimes it's fun, like, okay, Piles gave some proof. He said that for t less than 0.8 in some units, there is spontaneous magnetization. I can improve it to t equal to 0.97 or some such thing. So these kinds of results, which are called incremental results, are certainly possible, and they are not trivial. I mean, if you try to improve a given result, you will perhaps have to find some new way of thinking to go beyond what other people have done. So it's an interesting exercise, which I certainly encourage you to try to do, see how far can you go. There is a possible upper bound, which is the true critical temperature. You can never go beyond this. But can you go as far as that? I'm using bound, so I doubt if I can go above as far as that, but if I can go up to 5% of the TC, I'm pretty happy. If I can only go up to 30% away from TC, then it is not so great. Okay? So, one can try to see a bit better than whatever people have done. And let me stop here, and we can use the next few minutes to, if maybe I have some stuff written after this. No, it is the end. So, so then we can ask you any questions you would like right now. Yeah. Yeah. Okay, let's just go back. Now, we mark a hypercube. The probability that all the cubes are absent is q to the power 2dl to the power d minus 1. 2dl to the power d minus 1 is actually the area of the surface, right? So that factor 2d was just put in because it's easy to actually put in that factor. And that's the bound. So this is alpha is less than 1, but I am saying that, so that is, so that is means the number of sides in the cluster. Sorry, I've just, this last, the sentence is not well constructed. Here, that is bigger than S means that cluster size is bigger than S. So then the actual lattice should be a little bit bigger. If I make the hypercube of volume 2S, then I'm sure that the cluster will be of size S. Okay? Okay. So the other home assignment, which is not listed here, but I already orally mentioned, is that you actually have to read the Redner's proof program and work through it and check that it works. So there is actually a Fortran program written, and you can run it. You can take the square lattice and run Redner's program, and in 1 second of the computer time now, it will generate clusters of size 10 or 15 or some such thing. It's very efficient and very good. And of course, I can give a hard assignment, which is improve upon Redner's program. Okay? It will not be easy, but it's certainly possible. I don't think he will claim that this is the best program anybody could ever write. Okay? So if you can improve on this, that is really great. It is. Yes, sir.
Are there other algorithms apart from
They are variations of the same. There is a lot of freedom of choice, how do you choose the, I made this assignment rule, n bigger than E bigger than S or whatever. You can make some other assignment. You can make an assignment which is different at different sites. At this site, n is bigger than E bigger than S. At that site, S is bigger than E bigger, whatever. Or some more complicated route which depend on previous history. But in the end, there should be a unique rule which tells you, there should be a priority rule. So all the algorithms will break down into giving the priority rule. You can choose totally different representations of clusters, like I will give you all the sites. I don't care. Coordinates of all the sites, and then alphabetically order this list, and then alphabetically order the list. That's a different representation. It is less efficient, but it is certainly different than this. So by the same token, you can choose a different way which is better than this. I'm not aware of anything which works better than this.
How does the time scale with the size for this algorithm?
It's all of them are actually efficient in the sense that time scales at the number of things you count.
That's exponential.
It is exponential, but that is bound to be exponential. If you are doing brute force counting, then each cluster has to be counted once, then it has to be generated once. Then the time to generate a single cluster, which is, you have to check that it is allowed or so on, is proportional to S. So the time to generate a single cluster you have to keep track of, and you write an algorithm which takes less time to use here. And then each cluster has to take one step to count at least. Okay. The algorithms which are better than this, we will discuss tomorrow, I think. They use recursion. So then you don't count one cluster at one animal at a time, you count classes of animals together. Then sometimes you can do much, much better. Sometimes you can get the exact answer for arbitrary S in finite time. But that is not brute force enumeration, that is just a smart way of counting. So for particular problems, you can get smart algorithms which or smart answers which calculate the final answer. But it is not a general purpose algorithm for all possible lattices or some such thing. Okay, so let us stop here.